Welcome to the fourth lecture in the OChem series. This corresponds to Thursday of the first week, the first part of the lecture. Going to cover this time bonding. So just to reiterate what we've done so far, we've done the honk rule, which says hydrogen forms 1, oxygen forms 2, nitrogen forms 3, and carbon forms 4 bonds in a neutral species. From there, we looked at formal charge. When it deviates from that, what kind of charge it'll carry. We've looked at hybridization. We've looked at structure. We've looked at Lewis structures and how things are connected. We've looked at molecular structure to figure out the exact shape around central atoms. So overall, we're having that's a carbon that we are too lazy to write in as chemists. And you are assumed to know the honk rule, meaning if I consider, let's say, this carbon, let's just arbitrarily pick a carbon here. That carbon has 1, 2 bonds, 3 bonds. So there's an unwritten H that's on it. Same thing here. This carbon has two bonds with a double bond, third bond there. So it also has a so-called unwritten H. Because it is a double bond, then let me go ahead and inventory. I know I have an S, P, and a P to choose from, but because of the pi bond there, I pi that out. So that must be an sp2 hybridized carbon. When I consider, let's say, this carbon down here, it has 1, 2 bonds, so it must have 1, 2 more bonds to H's. They're all sigma bonds, so it's going to be sp-p-p. So this will be sp3 hybridized. So as stressful as this thing may be, a bigger molecule, it's still the same simple things when we look at atoms. This is a skill you're going to have to be able to do on the exam and homework just throughout. So you have to be able to recognize this point as a carbon, what hybridization it is, what structure it'll be. So if it's sp2, like here, 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 and so forth, it's planar, trigonal planar. So if you have a bunch of planar things next to each other, this overall group is planar. Overall group is planar. And then if sp3, can't read my own writing, that's embarrassing, then it's going to be three-dimensional. One H will stick out, one H will stick back, and it'll fold in a way. And again, that's going to be something we look at down the road. But I want to emphasize the molecules I'm going to try to throw at you have biological significance. So catechins are free radical scavengers. That's what I'm going to call them in OChem, which probably doesn't mean anything to anybody. But if you take biochem or cell bio class, they talk about something called antioxidants, things that can pick up loose electrons on oxygen. That's what this compound does. When you have lots of double bonds together, you can pick up an extra electron and share it within that network. That'll be something we'll cover towards the end of this course. But I just always want to throw certain classes of molecules. So it's a free radical scavenger. OChem word picks up something that has a single electron. It's called a radical. Scavenger means this picks it up. But in bio, we call it antioxidant. So if you eat a lot of green leafy vegetables, get a lot of catechins. Catechins are healthy because they prevent you from oxidizing away, from aging too fast. Okay, let me get rid of all I've written because I'm going to ask those same questions. Which carbons are sp2 hybridized and which ones are sp3 hybridized? So if I look at the double bond here, 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 and here, that means if it has a double bond, again, I want to do my same system, spp, but to get rid of make a pi bond, I got to get rid of a p. It's going to be less with sp2. Anything that doesn't have that, no pi bond, no pi bond, no pi bond. So I'm going to fill it in. These are all sp2 because of that pi bond, the second bond and the double bond. These are all sp2 because of the second bond and the double bond. And then these are all sp3 because there is no pi bond involved with it. You are expected to be able to identify that. So you're also supposed to note that this oxygen, also because it has 2 single bonds, is sp3. This OH is sp3 for now. We're going to consider it sp3 because it has 2 single bonds, single bonds, single bonds. So at our level, you need to be able to identify it. But this question asks for which carbons are sp2 and which carbons are sp3. Okay, so hopefully this hybridization is making sense. It's also making sense of the structure. So where this becomes kind of interesting is if everything is planar and everything is planar, planar things, a flat item can slide into cell membranes much more easily. So a lot of times you're going to notice structures will have features that do two things, either react or slide into a space in a biological molecule and anchor it and hold it in place. So a lot of our molecules we'll be interested in will have anchors and then reactive sites, anchors and reactive sites. And we'll get into that again as the course goes on. Bonding. So the actual type of bonding, I want to really emphasize that, again, we're looking at bonds that have two atoms, each delivering one electron. So the bond type is going to be called covalent because it's shared equally. However, there are some bonds where one gives two and one gives none, so a negative and a positive, and maybe they share, maybe they don't, known as ionic. But for our purposes, we're going to consider sigma bonds to be a covalent bond because it's organic chemistry. We're going to focus strictly on covalent, and we're going to distinguish sigma bonds where electron density resides between the atoms, between the two nuclei, and pi bonds where electrons are in overlapping p orbitals, in horizontal and vertical versions. Bond length, the distance from one nucleus to its neighboring nucleus in a bonding pair. Notice it says the average distance. So I want you to think for a moment and why you say why that is, and I'll give you the answer in a second, or you can just pause and I'll have it. But the reason they call it the average distance is all atoms are constantly vibrating, they're constantly in motion. So two atoms might come together a little bit, pull apart, come together, pull apart. So average distance is based on where they are in their average vibration. Okay, the bigger the atom, the longer the bond. The hybrid, more S character, the shorter the bond. So again, more S character, the more S shorter it is, the more acidic it is, and the more stronger it is. Bond strength, the energy it takes to break that bond. Stronger the bond, more energy I put in. So we're going to learn a term called the bond dissociation energy. Dissociation is the breaking apart. So you've heard of an association where people all come together and join. Dissociation is the exact opposite, where they break apart. So the energy you put in to pull two atoms apart, that is known as the bond dissociation energy. A stronger bond takes more energy to break. And again, free radicals are single atoms. So if I go from like a carbon-carbon situation to unpaired electrons, a single electron, that's called a free radical. That's a free radical. That's where that term is coming from. It's going to be introduced more formally in chapter, it'll pop up a little bit in chapter 3 with resonance minimally, but eventually will show up more when we start doing alkane chemistry later on in chapter 9. A little bit in 8 actually as well. Finally, bond polarity. Polarity is the distribution of electrons, how much you're on one side or the other. So it's known as a partial positive and partial negative. So you probably learned this at some point in your GChem travels, that chlorine is more electronegative than carbon, which means it will get a delta minus, and this get a delta plus, meaning chlorine, once electron holds onto it a little more tightly, and has what's known as a polar covalent bond. Electrons are shared unequally, a little more in chlorine than they are in carbon. I'm going to toss this out here early. We're going to use it a lot this class, but you have to know that if you don't know your relative electronegativities, you're full of Funkelbrüche. Don't be full of Funkelbrüche. So Funkelbrüche is our mnemonic for the relative electronegativity of elements common in organic chemistry. Fluorine beats oxygen, which beats nitrogen, chlorine, bromine, and so forth. So Funkelbrüche. So because chlorine is more electronegative than carbon, it's going to be delta minus, carbon will be a delta plus. If I had a bond between O and I, O would get the delta minus, I would get the delta plus. Okay, so I want to go ahead and look at that a little more detail. Periodic table is going to help me. Again, I want to point out when I go left to right, they get smaller. When I go down, because of more shells, they get bigger. Okay, perfect. So left to right depends on Z effective. Larger to smaller is kicked in, so I can erase that. Top to bottom, size as well. So for instance, a CC bond, large and large, is longer than a CN, large and medium, which is longer than a CO, which is large and small. which is longer than a NO bond, medium, small. So if I consider very big, big, medium, small, and very small, I can predict relative size. Top to bottom. So again, let me erase my drawing because it's just getting in the way of a prettier computer picture. Same sort of story. CI is longer because same atom in each case, carbon, but big atom, medium atom, small atom, really small atom. So longer bonds generally are easier to break because the electron density is further from nuclei. So we're going to discover that a carbon with an iodine is typically more reactive because that bond is longer, so it breaks more easily. Longer bonds are typically weaker bonds. So this is going to be good at breaking. So carbon with an iodine is going to be highly reactive. Bromine is going to be pretty reactive. Chlorine is going to be reasonably reactive. Carbon with fluorine, not as reactive as the other three. So if I want to look at a molecule like this, I want to add one more piece to the puzzle. So atomic size impacts the bond length. So does hybridization. So I want you to take a moment, like pause the video and figure out what the hybridization is of each of the carbons in here. And based on S character, make a prediction of which is the longest and which is the shortest carbon-carbon bond. Okay, so hopefully you paused it, you did that. This is a bond between sp3 and sp3 because they're 4 sigma bonds. So that's going to be my longest. This is between sp3 and sp2. So sp2, more S character, more shorter. So it's going to be a little bit shorter. And then finally, the shortest one of all, sp2 to sp2. And then comparing this one here and this one here, I can't really compare them. But this will be my longest. This will be my shortest. And this will be my middlest. Okay, feeling pretty good about this. So longest CC bond, shortest CC bond, middlest CC bond. Okay, I think I have this. I think I'm getting the basics of it. This is where it's really important. If you want to do well in this class, this is one of those checkpoints where you have to go back and make sure all this stuff is clicking. And more importantly, can you take different examples? So take the ones I give here, see the trend, but could you do the same thing for this row? Could you do the same thing for, instead of carbon to these halogens, could you nitrogen to, let's say, these chalcogens, these chalcogens? Maybe, we'll see. Okay, covalent bond strength. Again, longer bonds or weaker bonds. That's going to be our general notion. It is 99% of the time true. There's going to be a few exceptions, but it's going to be pretty true. So the bond length is 2.13. I know iodine is really low, periodic table. And I just realized the lecture room has no periodic table. So you're just going to have to trust me on this one. Cl, Br, and I. Iodine, it's the longest bond because it's the biggest atom. So it's also the weakest. So if I do that same thing to Br, and I don't know if you can see the line. I try to make the line a little bit shorter, but it's really minute. But I want you to do that when you take your notes. If you start being really anal, really pay attention to the details, draw this line a little bit longer, draw this line a tiny bit shorter. So this is 21, this is 19, if you will. So it's about 10% shorter if I've drawn it right. Shorter bond, stronger bond. So before I draw the next one in, make a prediction. When I have a carbon CH3 group connected to a Cl, because Cl, it gets larger as I go down, so smaller as I go up, smaller atom, shorter bond. So it should be less than 1.93. So take a guess. And if you guess around 1.7, 1.8, you're in good spot. Energy, it's going to be higher than 69.6. The trend here goes up by about 13. So my initial guess is about 13. I'm going to see if I'm right. Went up by about 15, not bad. And this was around 1.7, 1.8, a little bit closer to 1.8. Perfect. I have a nice, easy decision to make here. Longer bond equals weaker bond almost all the time. Okay. The difference in what I've done here is this is an ethyl group, 2 carbons, instead of a methyl group, 1 carbon. So notice the bond length changes ever so slightly. It goes from 2.136 to 2.152. It's a little bit longer. That's partly because when you add more stuff, it crowds things and can push it away a little bit. Then also, we're going to learn that carbon, because it's closer to carbon electronegativity, they're equal than iodine. When iodine pulls electrons away, this carbon can push it in to help compensate. If you push electrons in, it makes it easier for electrons to move this way and get a little bit further away from carbon, makes it a little bit longer. Longer bond, lower bond energy. So again, make a prediction of what you expect, because the next one I'm going to do is the same thing with bromine in this group. So just like I went same group all the way down with iodine, bromine, chlorine, you can pretty much guess that's going to happen here. So in this case, with bromine, it's going to be less than that number by about this, or longer than this number by about the same much this amount this one went up. So this one went up 0.016. So at 0.016, it's going to be what, 1.95-ish? And then the energy is going to go down by about 3. So I'm going to say roughly 66. So 1.950, perfect. Just under 66. So it actually is a pretty good trend. This one, same story. I'm going to say this is going to go up to what, maybe around 1.80, a little over 1.80, and maybe around 80. 1.789, not quite the same amount, and then 80.3. So your job, whenever possible, is to guess where I'm going in a lecture before I do it. So introducing another new term. So this vocab list is going to get really expansive really quick in this class. Electron donating group. So when I mentioned that this carbon can share electron density with this carbon to compensate for this iodine, this bromine, and this chlorine pulling electron density away, because it can give electron to it, it's donating. So electron donating groups to C. So I'm going to call this an electron donating group, EDG, because it can share electron density, because H is less electronegative than carbon, so it gives a little bit there. That carbon can in turn give it to this one to help make up for what it's losing to the iodine. Electron donating groups put electron density in, which can repel the electrons here away, make the bond weaker and longer. Okay, so I'm going to push the trend a little bit more. Notice that this is carbon by itself. This is a carbon with one other carbon. This is carbon now with 2. And notice the same story. As electron donating group, now instead of just one CH3 on that carbon, there's 2 CH3s, so more donation. Bond gets a little bit longer and a little bit longer, a little bit weaker, a little bit longer, a little bit weaker. So I'm seeing this trend. I'm kind of happy with this trend. Fine, last group when I put 3 on there. So this is a methyl group, ethyl, isopropyl, and T-butyl. Not that you have to know those now, but if you happen to speak the language of OChem, we can distinguish those. So as I put more carbons on the carbon bonded to the halogen, notice that it goes from 56 to 53 to 51 to 50. Got smaller and smaller. And notice it went from 2.136, 2.152, 2.160 to 2.165. It gets longer. So the more donating groups, the weaker the bond, the longer the bond, almost all the time. Okay, so electron sharing, this is what's known as a tertiary. So I'm going to introduce this thought. Tertiary means it's a carbon with 3 other carbons attached. Secondary is where you have a carbon with 2 other carbons attached. Primary, you have a carbon with 1 other carbon attached. And then finally, this is called methyl, just because it's just a carbon all by itself, nothing else attached. Okay, so the last thing I really want to emphasize is the concept of unequal sharing of bonds. So we went, or uneven sharing of electrons in a bond. So mention the Funkelbrich rule, and if you don't learn it, you're full of Funkelbrich. F is more electronegative than O, O more than N, and so forth. So just want to see if you can apply it. So if we had a bond between F and O, F would get the delta minus, O would get the delta plus. Bond between O and N, O would get the delta minus, N would get the delta plus. This becomes really important because in biomolecules, you have a lot of O, N, and C's. And so N can behave in a whole bunch of weird different ways. And the difference of when it has a negative and positive is the difference of making and not making hydrogen bonding, which when you get right down to it is absolutely significant in biochem. CH, C is slightly more, so it's a very small dipole moment. C and BR, BR is more than C, so it's a much bigger dipole moment. S and H, S is more than H, so delta minus delta plus. OH, that's an even bigger difference. And so what we're going to run into, I'm drawing the deltas all the same size, but this becomes much more significant. And what we're going to learn is that because of this bigger difference in electronegativity, this gets to be a big enough delta plus that it can actually act like an acid and try to protonate something. It's not going to fully protonate, it'll form what's called a hydrogen bond. That's going to be absolutely essential to what we're going to predict in terms of solubilities and interactions with different atoms. So for now, I'm just going to leave it as delta minus delta plus. And N is more electronegative, so delta plus will be on the I. CF, F is more electronegative, so this will have a very large dipole moment, just like before. So I'm going to decide that's really big and that's really small. CCl, again, chlorine more electronegative, so typically carbon halogen bonds will have a delta plus on carbon, delta minus on chlorine. And OS, O is more electronegative than S, so delta minus delta plus. So 2 rules I want you to pay attention to. Number 1, the bigger the difference in electronegativity, the bigger the plus minus difference. And in organic chemistry, plus and minus, I always have to find it. If I have something negative, it's going to attack the positive. If I have something positive, it's going to attack the negative. So you can predict your reactivity if you can identify where the plus and minus is. This is going to be such an important skill. So the simple rule of being able to write Fonkelrich and decide which is more negative and which is more positive, more electronegative and more electropositive, it's critical. It'll help with everything. So for this compound right here, O is the most electronegative atom, so it's going to have the delta minus here, has what's known as a dipole moment. Because it has a dipole moment, pluses attract minuses, that means if another one of these molecules was in solution with it, which you can't really just have one single molecule, so it's always going to be surrounded by something, it can form this so-called polar interaction, delta plus, delta minus. So these start attracting one another. The bigger the plus here and the bigger the minus here, the better they attract. So it can hold it together, makes it harder for that molecule here to move away. So it make it feel thicker, more viscous, if you will, or might make the boiling point go up. It takes more energy to remove it. So it's going to have some sort of interaction between those two. I'm going to erase. And in the next structure, where I want you to make some prediction about its dipole moment. And a D is called a Debye. It's just a random unit of polarity. So the bigger the D, the more polar it is. Nitrogen is more electronegative than hydrogen. So this one's going to pull this way, and this way. And they're all going to add up to an overall dipole like that. So the individual dipoles will sum. Same thing, delta minus delta plus. This one's not quite as strong. And we'll learn why, because relative electronegativity, N is much more than H's. Oxygen is more than carbon, but there's 3 H's to be different from. But double bonds do something special. In fact, it's going to be a whole chapter. And finally, this compound is known as benzene. For benzene, this is really interesting because every single H is going to donate this dipole. But if you add up vectors, if you remember, vectors, so this vector going straight down is going to cancel one going straight up. This one up and to the left is going to cancel one down and to the right. Down to the left is going to cancel up and to the right. So all those dipoles cancel, and this one ends up being what's called nonpolar, no dipole moment. There's a phrase you're going to learn in OChem. You probably learned it if you took cell bio. Like dissolves like. Polar compounds like to interact with polar compounds. Nonpolar like to interact with nonpolar. This is a huge factor in the way our proteins fold. Hydrophilic are molecules that are typically polar and want to interact with their charges. Hydrophobic are ones that are typically nonpolar and want to get away from charges. And this is going to impact how a protein will, I guess, create its local environments. Okay, so we're going to take this at the next lecture for intermolecular forces. I'm going to stop here so I can make this bonding. But we covered probably about 80% of that Thursday lecture. So hopefully it went well. You're doing great on this stuff. And I will see you at the next, well, I'll see you at lecture and I'll see you at the next recording. Thank you. Bye.